Hello everyone, welcome back. We are going to tackle the FRQ portion to the Unit 1 and 2 AP Chemistry exam now. YouTube intros are so awkward. If anyone has a better idea than just saying, hello everyone, I feel so awkward when I do that. Are you ready to get your brain cows milked? I think is already taken, so don't recommend that one. But YouTube intros, let me know. I don't know what to do. I feel terrible. Anyway, let's get into it. So we are going to tackle the FRQs now. What color are we feeling? Let's do a red. Sure, red. We're probably going to have to fix this. Yeah, we are. So just reminder, FRQs, there is one long FRQ, one short FRQ, and you will get 32 minutes to do both of them. How you choose to tackle them is up to you. The general time frame is 20 to 22 minutes on the long, 10 to 12 on the short. So usually I'll call a 10-minute warning left in class. That's kind of your last opportunity. You should be moving on to the short at that point. So let's get going. What type of chemical bond is present in Cl2 molecule? Chlorine and chlorine. This is two nonmetals bonding with each other. Let me click the full screen. This is non-polar covalent is the type of bond. Now, the answer for the scoring guidelines, you just needed to say covalent. That's all they were looking for on that one. Non-metal, non-metal, covalent, metal, non-metal, ionic. Cl2 reacts with the element strontium to form an ionic compound. Based on the periodic properties, identify a molecule X2 that is likely to react with strontium in a way similar to how Cl2 reacts with strontium. Justify your choice. So let's go over to the periodic table. We're told, I still have some charges on here from the multiple choice. We're told that Cl2 will react with strontium, SrCl2. Checks out. What other compound is going to react with strontium like that? How about F2 or Br2 or I2? Any halogen would work for this case. So we just got to pick one and then run with it and also give a justification. So I'm going to say, let's use iodine. Iodine never gets enough love. So Sri2 will react in the same way. We are asked to justify, so let's come up with a justification. I and F are in the same family. They have the same number of valence electrons, and then I would also say therefore they will form the same ion, but I ran out of room and I can't write neatly because I'm running this on my screen and also trying to keep the camera steady. So something along the lines of that. See a graph of potential energy versus internuclear distance for two chlorine atoms is given below. On the same graph, carefully sketch a curve that corresponds to the potential energy versus internuclear distance for two Br atoms. So we're saying that this is a ClCl, and we need to draw a Br-Br. Alright, these graphs are a little tricky. However, they're a little complicated. There is only one thing we need to worry about. Where do we put the trough? That's what the that's what the scoring guidelines are checking. Is the trough lower or higher than this one's trough? And what I mean by trough is the lowest point. Is it further to the left, further to the right? So both are single bonds. The difference between Br and Br and Cl is Br is a bigger atom than Cl. We can see this on the periodic table. Br is further down on the periodic table than Cl is. So therefore it's a bigger atom. So just to visualize that, ClCl might look like this, Br would look like this. And we know, so first off, that already solves one of the things for us. Br is bigger, it should have a bigger bond. So let's just say we're going to put our bond there. For the energy, we know that the bigger a bond is, like the longer it is, the weaker it is. And on this graph, weaker means less down. It means a less magnitude. It does not dip down as far. So we should also draw it up. So I like to really exaggerate when I draw graphs like this. I like to leave no interpretation to the grader of what I am trying to do. Because if there's interpretation, that means they can interpret it wrong even if you got the correct answer. So I'm going to draw my trough right here. Let me zoom in a little bit. Not that much. Something like that. And then this is a 2-pointer. 1 point for to the right, 1 point for up. All right, let's go to part D. In the box below, draw a complete Lewis electron dot structure, electron dot diagram for the C2Cl4 molecule. All right, typically all the Lewis structures, not all, definitely not all, obviously not all, this one's not going to be one. Most of the Lewis structures have a central atom and everything is attached to that central atom. However, the one main exception to that is if you see a molecule that has multiple carbons, it is most likely going to form a carbon chain, which means we're going to have 2 carbons in the middle, and those 2 carbons are going to form the backbone for our structure. Let's put all the Cl's around it. Molecules like symmetry, so let's put 2 Cl's on each side and go from there. Connect everything with single bonds. Each Cl has 7 valence electrons, which means they want to form 1 bond to get that one last electron. Carbon has 4 valence electrons. It's going to want to form 4 bonds. So we need 1 more bond for each of these carbons. That bond is going to form in between them. Again, the way I like to do these Lewis structures is I think about formal charge while I'm doing them. Carbon has 4 valence electrons, wants 4 bonds. Chlorine has 7 valence electrons, wants to form 1 bond. This is what the molecule looks like. And we can count up the electrons just to be sure. Everyone's happy. Carbons have 8, chlorines have 8. Let's count up the electrons. Why not? All right, 4 plus 4 is 8. Chlorine is 7. 7 times 4 is 28. 8 plus 28 is 36. 36 divided by 2 is, I was doing so good, 18. 18 pairs. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Perfect. Everyone's happy. We've put in all the electrons we need to put in. What is the hybridization of the C atoms in C2Cl4? It doesn't matter which C atom. Both the C atoms are the same. I've now kind of cluttered everything. Let's just put it back a whole bunch of times. Nice. Go technology. All right. What is the hybridization of the C atoms? All right. We have 3 electron domains. 1, 2, 3. Therefore, it is sp2. Hybridization. What is the approximate chlorine-carbon-chlorine bond angle? So we're looking at the carbon as the central atom. Again, both the carbons are the same. 3 electron domains, 3 bonded atoms. This is trigonal planar. Oops, it asked for the bond angle, not the shape. Don't put the shape. It's 120. 120 degrees. One thing to note, I'm going to turn this mistake into a lesson. Don't put extra information. Don't ever put extra information. Once you've answered the question, that's all they want. The reason for that is if you give the shape, for example, and the shape is wrong, they might mark the question wrong because you put a bit of wrong information in there. They only want the bond angle, only give them a bond angle, even if it's a guess. Because if you give them the right bond angle but the wrong shape, maybe they mark it wrong. But if you only give them the bond angle and it's the correct bond angle, then you're good. And it doesn't ask to justify, so we're not. Lastly, is the C2Cl4 molecule polar? This molecule looks pretty non-polar to me, so I'm going to put no. Polarity can come from either asymmetry in shape or asymmetry in distribution of atoms. There is no asymmetry of shape. Both sides are like balanced. This molecule looks pretty symmetrical. Trigonal planar is a shape that can cancel out dipoles. And then all of the appendages, for lack of a better terms, are chlorines, and they're all the same. So that is non-polar. And all we really need to say here, because explain is this is a kind of awkward one to explain, as I'm just going to say like something like the dipoles cancel out due to the symmetry of the molecule. Good. I promise my handwriting's not that bad, normally. Maybe when I'm lecturing. Sometimes it's pretty bad on the board. A compound composed of carbon, chlorine, and sulfur has a molecular formula CCl2SN, where N is an integer. If the mass of 1 mole of this compound is 344.3 grams, what is the value of N? So this is one way to write a molecular formula, where the empirical formula is in the parentheses, and this N stands for what we're multiplying everything in the empirical formula to get the molecular formula. So we know what the molecular formula molar mass is. 1 mole is that many grams. So let's find what the molar mass of the empirical formula is. All right, carbon, I know that one by heart. That's 12.01 grams per mole. We are no longer in multiple choice, so let's use the exact ones because we want exact numbers now. Chlorine, it's probably one I should have memorized, 35.45, but I'm not confident to the point where I'm not going to check that. Sulfur, like 30 something. Let's go and check them. So to the periodic table. All right, chlorine is 35.45. Woohoo, go me. I do deserve to be a chemistry teacher. Sulfur is 32.06. So let's go back to the chemistry workbook. Full screen it, get away from the multiple choice. We've already been through that. .06 grams per mole. All right, 1 carbon plus 2 chlorines plus 1 sulfur. 12.01 plus 35.45 plus 30 plus another 35.45 plus 32.06 is 114. CCl2S is equal to 114.97 grams per mole. So this is 114.97. This is 344.9. Let's take 344.9 and divide that by 114.97. 344.9 divided by 114.97. And that is 2.9999, so that's like 3. So what that means is this N has to be 3. The molecular formula is CCl2S parenthesized 3. N is equal to 3. The molecular formula would be C3Cl6S3. But we don't have to put that. It's just looking for this. All right, let's continue. Was that actually all of the first one? That was all of the first one. There's another 2-pointer in there. Where is the other 2-pointer? Oh, this one was a 2-pointer. The drawing one was a 2-pointer. You got 1 point for the correct number of electrons and 1 point for the correct structure. So I'm glad we double-checked the electrons because there's just a point associated for putting down the correct number of electrons, regardless if we got the structure correct. All right, 3 stable isotopes of Mg are Mg24, Mg25, and Mg26. A rock sample from another planet has a different distribution of 3 stable isotopes of the 3 stable isotopes that are found on Earth. A partial mass spectrum for the Mg on the rock sample is shown below. So, one thing to know about those molar masses on the periodic table, they're based off Earth. So one thing that they like to do so you don't rely on the periodic table for these answers, because we know that these graphs are just like they average out to the molar mass on the periodic table, is they'll say, oh, this comes from another planet or a space rock or, I don't know, another dimension. So, A, draw a line on the graph to show the mass of the missing isotope and its percent abundance. Let's see. So, we know that we have 3 stable isotopes, Mg24, Mg25, and Mg26. The 25 and the 26 are already accounted for. The one we're missing is the 24. We also know that the percent masses need to add, the percent abundances need to add up to 100. So we have a 40 and a 20. 40 plus 20 is 60. That means we're missing 40%. That other 40% is going to go right at that 24. That's the answer. Use the completed mass spectrum to calculate the average atomic mass of magnesium on the other planet. This one, I really don't even need to do the calculation before. I know that the average atomic mass is just going to be 25 AMU, or 25 grams per mole. 25 AMU. That is because, like, look at, the average is 25 perfectly. It's a weighted average, but we have exactly as much percent above 25 as we do below 25, so the average will come out to 25. On an actual test, if I had time, I would go back and I would actually do the calculation. It would be 24 times 0.4 plus 25 times 0.2 plus 26 times 0.4, and that would come out to 25. So you can do the calculation as well. The first ionization energy of magnesium samples found on Earth experimentally is to be 736 kilojoules per mole. If a similar experiment is conducted to determine the first ionization of magnesium in the rock sample from another planet, will it be greater than, less than, or equal to the first ionization energy of magnesium found on Earth? Explain our reasoning. So kind of a lot there. Let me reread it again. Not going to lie, that one kind of went in one ear, out the other. Okay, so it's saying that on Earth the ionization energy is 736. And it's asking, will the ionization energy of this magnesium on this other planet be greater than, less than, or equal to? It's just going to be equal to. Ionization energy doesn't depend on neutrons. Isotopes, these are isotopes. Isotopes are same protons but differing numbers of neutrons. But the and it also says isotopes too. Ionization energy is based off of electrons and protons. It's still magnesium, so we still have the same number of protons. And since it's all neutral, we still have the same number of electrons. So therefore, the ionization energy is going to remain the same. So equal to, and the reason is still has same proton and electron count due to it still being magnesium. Magnesium always has 12 protons. It has to. That's what makes the atom magnesium, is 12 protons. We're not changing protons, we're not changing electrons. The only thing we're changing is neutrons here, and they don't affect ionization energy. D, a table of successive ionization energies for magnesium and an unknown element is shown above. Predict the identity of the unknown element. So whenever you're given a list of successive ionization energies, the question you should ask yourself is, where does the big jump occur? For magnesium, it occurs in between the second and the third. We take a big jump from second to third. That's because magnesium has 2 valence electrons. So we can remove 2 relatively easily, but once we remove from the third, we're removing from the core. This unknown element, the big jump looks like it occurs between the first and the second, which means we can only remove 1 valence electron. And once we try to remove the second, we're removing from the core. The other thing is, these are relatively similar magnitude. So we can also infer that they are in the same period of the periodic table. So we're looking for an element with 1 valence electron in the same period as magnesium, which is sodium. Sodium is the one with 1 valence electron. So let's go back. The answer is sodium. We do not have to justify our reasoning here. Notice how it doesn't say explain or justify. So we're not going to justify. Don't need to do that. We can only hurt ourselves if we explain or justify when we're not asked to. You can't help your case They're just looking for this. I'm just looking for that. All right, and that is the FRQ. Hope this helps, but obviously, if you're watching this and you're still confused, feel free to ask me during class. But the reason I do this is because I know sometimes you don't want to ask me during class, or sometimes you're studying on Sunday night and the test is Monday morning and you can't ask me. So that is it. I will see you all in class. Good luck in the rest of your studies.